Welcome back to Integral Calculus. In this video, I want to introduce you to the techniques of numerical integration. The idea behind numerical integration is that we can use a computer to approximate the value of a definite integral, that is an integral that has a numerical value, not a symbolic integral, whenever we don't really know how to deal with it by hand. The idea here ties back to the basic understanding that an integral is related to the area under a curve. At some point in your previous study of mathematics, you have almost certainly been introduced to Riemann sums. You may or may not remember the name. That's okay if you don't. But the basic picture here is something that you should at least have some memory of. All right, so if we have a function, something that looks kind of like that, and we want to integrate between 2 points, let's call them A and B here. The way we can understand this integral is that we can break this region up into a whole bunch of spaces. And then we can take each of those columns and we can form a rectangle. You may remember the left-hand rule, where you use the left side of each bar as a way of constructing the rectangles. You may remember the right-hand rule, where you use the right-hand side of each bar as your tool for constructing those rectangles. My personal favorite has always been the midpoint rule. Find the middle value, right, the value of the function right in the middle of that interval, and use that. I think that gives you a relatively close approximation, because in every single bar, you tend to end up with a little bit that's too high and a little bit that's too low. If you were going really fancy, you may have come across what's called the trapezoid rule. In the trapezoid rule, you connect end to end. And now, instead of having rectangles, you have a whole bunch of trapezoids. And the volume, or the area of a trapezoid, is 1/2 b1 plus b2 times h, where in this case h is going to be measured that way, and b1 and b2 are going to be measured this way, so it would be 1/2 f of xi plus f of xi plus 1 times delta x. And then if you stare at that for long enough, you realize that you can actually make some simplifications out of this, right? xi plus 1 is going to become xi in the next term, and you've got this 1/2 that's kind of going to cancel out when you add all of these things together. And there's a fairly nice formula for dealing with the trapezoid rule by hand. But I really don't want to deal with the trapezoid rule by hand, because that's still a whole lot of writing things out and a whole bunch of doing calculations. And it's the same formula over and over and over again. Luckily, we have a device called a computer that is designed for doing the same thing over and over and over again. And so that's what we're going to be using here. All right, here I am in the free web service Google Colab. It's Google Collaborate. And it is a notebook interpreter for the Python programming language. If you have never done any programming before with Python or with any other language, please don't panic. This is going to be so easy that you can do this without any programming experience whatsoever, because I've done almost all the work for you. All right, I am going to share a link to this notebook. You are free to copy it and edit it as you see fit. You might see up at the top, this notebook is in playground mode. Changes will not be saved. That way, the version that you see is going to be what you are seeing here as I start into this, not what happens after I deal with things. But I do want to point out that if you go into the File menu, you can save a copy to Drive. Right? So log into Google using your school-issued email address, and you can save a copy of this and you can edit it. You can save another copy and you can edit it to do something different. And I also want to point out, where is it? You can print this, and depending on how your computer is set up, you can probably print to a PDF file. PDF files are really great for submitting electronically, or you can literally print it on paper and deal with it from there. All right. So the very essence of programming is that somebody else has built powerful tools, and we can copy those tools and use them to our advantage. Specifically, I'm going to start with the programming language Python, which is a relatively easy to approach language. And then I'm going to import some things. You can see in this first block, marked very clearly, do not modify this section, from math import star. That gives us access to mathematical functions, square root, sine, cosine, logarithms, natural logs, all those sorts of things. And then the big one, the one that we're going to be using to carry most of the weight, is the SciPy Integration package. Right? The scientific Python programming package has a whole bunch of numerical tools that are special built for certain purposes. The SciPy Integrate package is special built for doing numerical integration. There are a number of different packages, a number of different tools for doing the numerical integration. In this video, I'm going to stick with the trapezoid rule because, well, we understand how it's supposed to work. But I don't want to try to give you the impression that the trapezoid rule is the best or the most appropriate in all circumstances. It's just a method and it works. Right. The text here that you can't probably read because the screen is too small gives an explanation of what we're going to be doing. And then we have another block that says modify this section to represent your integral. So I have a function set up here. I have pi times the quantity x minus x to the fourth power. Right? That's not that bad of an integral. That's probably one we could do by hand, and that's kind of what makes it a good first example. Then I have my limits of integration, in this case 0 and 1. And then the last thing I have to choose is the number of steps. In this case, I chose 10,000. The more steps you choose, the more close your approximation will match the actual value. But the more steps you choose, the longer it will take to run. Generally speaking, 10,000, 100,000, and 1 million are used for most scientific purposes. I'm doing all of this on Google servers, not on my own server. So because it's a free service, they don't have a lot of wiggle room for timeout. I'm going to stick with a relatively small value. If I was doing this on my personal computer, I probably would have picked n equals 1 million instead. All right. And then the last block of code sets up the algorithm. It tells the integration tool how to understand the integrand. We're not going to worry too much about that. As it says here, do not modify this section. All right, I have a number here because I've already run this notebook to make sure that it works, but it does say down here, after the changes you've made, click on the Runtime menu up at the top. And then if it is available, you want to restart session and run all, which is right here. In this case, it's not available because I haven't run this session yet. So I will just choose run all, which is the first thing. But I do want to stress that if you are modifying things and changing things, sometimes Python will remember the old value and it won't give you the most accurate result. So if you've used the notebook once already, you want to make sure to restart and run all. Right, but I haven't yet, so we'll go ahead and run all. It changes these icons to these play icons as it churns through the code. It shouldn't take all that long. And it gives us a value down here at the bottom, 0.9424777, etc., etc. All right, let's jump back to my notebook and hit the right buttons. There we go. And so this particular example, we were looking at the integral from 0 to 1 of pi times x minus x to the fourth power dx. That's a fairly straightforward integral. We absolutely can evaluate this by hand. Right, the pi is just a constant. We can kind of ignore it. Integral of x is 1/2 x squared. Integral of x to the fourth is 1/5 x to the fifth. Plug in x equals 1. We get 1/2 minus 1/5. Plug in x equals 0, we get 0. Right? And 1/2 minus 1/5 is 3 over 10. So I get 3 pi over 10. Or, if I grab my calculator out, 3 pi over 10, my calculator tells me, is 0.9424777. Well, that number looks familiar, doesn't it? 9424777. The next digit my calculator gives me is 9. In the numerical approximation, we got a 3 there. So that is a very good approximation of the true value without that many steps. The field of numerical analysis is a rich portion of study in the overall landscape of mathematics. Numerical analysis certainly is about developing the tools for doing this sort of calculation. But more than that, it's for understanding how good the tool is. For a given number of steps, how far away in worst case scenario will your result be from the true value of the function? I would love to get to spend a little bit more time talking about those sorts of considerations, but for the sake of time, I don't think that that's going to be reasonable. Instead, we'll just focus on understanding this basic idea, right? Computers can be used to evaluate integrals numerically. The SciPy library is a fairly accessible way of doing just that. So I would like you, oops, that's not the button I wanted, that's the button I wanted. I would like you to look at the integral from 1 to 7 of x squared times the sine of x dx. This integral is something that we absolutely can calculate by hand. But I don't want you to calculate it by hand. I want you to use SciPy Or if by chance you're familiar with a different numerical library, you're welcome to use that instead. But I want you to approximate the value of this integral with 10,000 subdivisions using the trapezoid rule. Right. Take a couple of minutes, make sure that you understand how this works, and I'll see you in the next video.